Hello world, my name is Alan. We're practicing LeetCode, month 2, level medium. So let me share this problem. It's from the 75, top 75 list. And I have this pen, I have another pen, which I can use for my notebook when I will be drawing that tree. Have I started the counter? Clock, the clock. So let's see what we have. Problem 437. Path sum 3. Today is 25th of October. Given the root of a binary tree and an integer target sum, return the number of paths where the sum of the values along the paths equals target sum. The path does not need to start or end at the root. At the root or a leaf, but it must go downwards. The path must go downwards. That is traveling only from parent nodes to child nodes. Okay, that seems to be a little bit easier than, because there is only one direction. Upstream or downstream, upwards, downwards. And we need to find the number of paths. Okay, let's look at the examples. Target sum is 8. So we have this tree, 5 plus 3, okay. And we have 5, 2, 1, okay. And this is also 11 and minus 3. And that counts as a sum. And values could be from this range, and the target sum is within this range. And the number of nodes is up to 8,000. Okay, let me see. I don't have an immediate answer, but let's see, and let's look at some brute force maybe. So let me draw that. And there are three cases, 3 paths. So we have 10 at the root. Then we have 5. And then we have minus 3. I'm learning to draw the trees. And then we have 3 and 2. And by the way, they're not unique. The values are not unique. learn to draw trees. It's kind of tricky sometimes. It sometimes get tricky to draw a tree, and it's just good to. So, and in this case, when target is 8, target sum 8, yeah, we have these trees. We have these trees, these subtrees, essentially. Well, they are paths. Yeah, it's not like just a tree, it's a specifically path, yeah. And this 5. Now, I think if there was another node here and it was 0, then the sum would still be 8, and that will be another path. That will be a second. That would be a next path to count. Yeah, if we have like basically all the zeros that next to the target path, target sum path, they all will create they're all target sum as well. Separate, right? Separate, because that path is target sum. If with the another 0, that's another path that's target sum. Okay. Let's see. If we go depth first search, go over that tree. And yeah, when we go from a node, when we go from a specific node, the brute force would be, we start from 10, we go we count 10, count 5, then we count, we check if the sum is 8 or not. Count 3, we count, yeah, we just add to that sum 3, then we add to the sum another 3, and we never found the target sum there, so we go back, try with -2. We just do backtracking. We try -2, it's still not target. We try without. So basically, as we can see, any sum here that includes 3, that includes this root 10, will not find. We will not find a target sum. For this specific root. And And we can go over the entire tree and we can say like, okay, we're done with this one. Let's try another one. And let's count. And then we'll find, okay, 5, 3 will, detected, target sum, counted. Okay. Tried this and that, then tried that and that. So essentially, if we do depth first search for each DFS, for each tree and subtree, we can detect those target sums and count them, yeah. But that will be sort of, for each node, we'll need to go over the entire subtree. Sounds like a little bit n square-ish. So for 10, we'll traverse the entire tree. For 5, we'll traverse the rest of it. Yes, the tree gets smaller. So this is like, on average, half of the tree. And this is on average half of the tree. Another case is the entire tree is just one linked list. So we'll essentially, and by the way, that's not the worst abstraction or way to look at it. Because essentially, yeah, if we have just, we simplify that to a linked list, because we don't really need to go to the branches. I mean, each of them is a linked list, essentially. So yeah, along that list, we just need to check that. We need to check the entire list from 10 till the end, from 5 till the end, from 3 till the end. So that is n square. But n square with this number of nodes is not that bad. It's not that bad. So it might be a viable solution here. Just do n square. Yeah, traverse the tree with DFS, and then from each node, go do this search. There might be a way to do that search within one traversal, but then we will need to do, okay, we'll start the counting from 10. We'll keep track of the sum for 10 for this node. Then we need, as we get to 5, we need to start tracking the sum for 5. So one idea is, okay, we start, so we're at 10. Then we are at 5, we start, 10 becomes 15. Yeah, 5 is 5, then we have 3. 5 becomes 8. And 3 and 15 becomes 18. 18. So that if we have that list of sums, carry that list of sums along the way and check if any of them is at each node all the nodes that are already above, in that, yeah, we'll track their sum. Yeah, so then another 3, and that 3, yeah, so then we have another 3, that 3 becomes 6. And by the way, when we have 5 plus 3, we detected an 8. 8 detected. Then 3 plus 3 is 6. And but that means we need to track this list of sums, which we will, so basically to each number in that list, it started with 10, then 5, then 3. We'll be adding those numbers along the way. So each of this number needs to be added, like, yeah, essentially it's 10 plus 5. Yeah, we add the number to a list, and every new value is added to all the numbers in the list. And when we are done, when we hit a leaf, we pop that value. We can call it a stack and pop that value from the stack. Yeah, the last value, just we pop that. So yeah, if we use some extra memory, but also we would need to run for each node. We will need to run around that stack, that list. All right, because yeah, we need to, well, the longer the branch, yeah, like at worst it is 8,000. So for each of them, we'll need to run over that list and add its sum, and add the sum to it. And keep and update the sum, yeah, which sounds like an n square as well, but with the use of memory. So DFS over DFS over DFS, that's about n square, yeah. But if we fast plus track the list, because we need to add, and when we add, we need to check, are we at the target sum? Yeah. Plus track sums list plus sums list. That's another n square, because I mean, because yeah, we need to go over that list to update it at every node. Basically, these are the like options that I'm thinking of. There might be some optimizations for that list, because it's sort of like a prefix sum list. sort of, I mean, it looks like but it will be updated. Yeah, it will be deleted. I mean, the lifts will hit the lifts. They will be then deleted. And by the way, when we hit the lift, okay, then we want to we need to delete that value from the entire list again. So it definitely sounds like an n square with some more hustle. But given the number of nodes, it's just 1,000. It looks like this first option is a bit less. A bit more. Well, it's better because n squared time. But this also needs n memory. Yeah, memory. Yeah, but this one doesn't. So big O-N. All right. Okay, I think we kind of figured out the there might be some other ways, but I just don't see them clearly right now, immediately. And then this n squared solution seems to be pretty okay. All right, so how do we do that? We need the DFS function to search for those sums, starting with the root. Yeah, and then we'll do the function that catches the roots. But essentially, so we need to traverse over each root. And then for each root, go over the subtree. Yeah, there's definitely tons of repetition. Definitely. Well, n square. Yeah, for each node, we will go over each. Yeah, for like each node, we'll be visiting all the subnodes. Like 10, 5, 2, 2, 2, pew, 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 3, pew, pew, pew. Mario, do, 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 pew, 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 pew. 5, pew, pew, pew. Let's start with a simple task. How do we go over those roots? And by the way, do we need to go over the lifts? Yes, we do. We need to check the lifts as well. It might be the sum. They might have the sum in themselves. So function DFS. DFS. Yeah, and we're kind of on timing. It took like about 20 minutes to figure out the logic. So we are short on time a little bit. Yeah, but variable DFS function will take the root. So that function will take the root and it will not return anything, will it? Because it will just do the calls. So DFS is a function. It just gets us that node. So it takes the root. Yeah, should we call it the root? It takes the root of the tree. We can call it node. It's okay already because there will be nodes. All of them will be roots of the next tree. So, but it's okay. We can call them nodes. Now, if node is nil, essentially we need to say return. If it's not, then we need to say, then we need to call that search, that there will be a function that's like that, that's well, this DFS is, well, we can call it just DFS. We just need to get us over the nodes, and this one we can call the count sum, target sums, path sum. Count path sums. That function, yeah, will be called, and with this node, if it's not nil, yeah, and we need then to call DFS for node left and node right. That's kind of the basic. And we could probably move that function out of this nested function. Why? Because we need access to anything else. We just, in this, yeah, we just call it, and we, in this function, we will be passing that node to another function. Well, that another function will actually do the counting. And it needs access to target sum. So there will be this count sum. I wish, and it will take root. I don't know, we can call it still node. It's, yeah, but it's gonna be a root of the subtree, you know. So essentially it will be, but then it will be also calling them calling them. So we could just call them all root instead of node. Yeah. So because it's so to avoid the confusion, yeah. Now, that's the definition. So this path sum takes the root and its count, its path sums count target path sums count is gonna be 0 initially. And now we have that function. That function will take the root and it will do this, essentially backtracking. If root again is nil, return nothing. If well, we do need to have this track this this target sum, target sum. We need to track the count. We can pass it to the next call. Pass it to the next call. So each call will only see, yeah, we can use the count, so, or the sum, integer, and sum. So when we call the root, we'll pass 0 initially. And when we call this function, but then what we need to do, we'll root value. We'll add that value to the target sum. Oh, no. No? Yeah, given it's not nil, we don't want to check that value before. So yeah, so we are in the node, and in the node we add this value, we check, yeah, if no, that's not what we want. We want to just sum is what this current sum is what we're tracking, adding the roots, and if sum equals target sum, and I mean, we can call it current sum for If that's happening, then we update the counter, this target path sums count. And we call this function with root left and root right. And then we return. So that should be it. So how this works, we have a subtree, we have a, so this 10, if it's not nil, it will be added to the sum. Okay, if we detect a target sum, we count it. We call the children. Okay, if the left one comes, okay, if it's not nil, it's added, it's checked, and so on. Yeah, this should be working. An expected function. Oh. Yeah. So the syntax mixed and unnamed parameters. Oh, okay. So teacher, I need to be more yeah, what is the problem? Undefined. Oh, okay. At that moment, this variable is not defined. So this function essentially should be defined. Yeah, and this DFS is called after. Sum. Target. Some typos, but not enough arguments. What do you? Oh, okay. Yeah. So this current sum. Yeah, we need to call the current sum. There is some. Yeah, there is like. Yay! And it works. Multiple typos, but I mean, overall, it's a working solution. Wonderful. Well, 40 minutes. Within 40 minutes, I would say if we just jumped on it immediately, we would do it faster without evaluating the time complexity for the alternative solution that would do the DFS just once, but it would have to do other things. There might be some optimizations. We have sort of similar functions here, but they're at the same time different. They are a bit different. So I don't know if we actually can, I mean, there are some similarities, but if we can make a generic function, one without this search for target, one with, one without the path sums and one with, if we can combine them, I don't know. But overall, that's a solution for a medium level problem within 40 minutes. We'll see, we'll probably do a couple of more problems today. But this one solved good. I think for an interview, it should be a little bit faster. This might come as a warm-up problem, and then you need to do it like within, I don't know, 20 minutes should be better. So if there is a harder problem after that, and you have an hour for both of them, so this could be a warm-up problem. Yeah, if we just look at it in a simple way, yeah. And let's see if there are, like, what are other solutions like? So this one clearly uses just one function. And so there might be some other better way more, but there is a loop in here. Yeah, so it looks like it's so there is an answer, there is a function we call a path is a slide. Okay, so it does pass the slide, adds the values, sum plus, yeah, if some answer is counted, so there is a list of values. It's called path. And it's essentially going, for each node is going over the path. So it adds, yeah, it's like it tracks the, yeah, let's, yeah, there is the root, there is the target sum, and there is the path. And it returns an integer. And the function is called solve. And it solve for, so it returns an integer, but it's, yeah, eventually we never care about the integer, but every time it returns the sum of those two integers. Interesting. So if root is nil, return 0, okay, and we append that root val every time. Okay, so we keep those, this 10, 5, 3. Okay, we know, and on every node, we say that sum is 0, so we restart the sum. Then we go over the path, starting from the end, and we say that sum is sum plus that path. So it will be like sum is plus 3, then 3 plus 3, 3 plus 3 plus 5, 3 plus 3 plus 5 plus 10. So the total sum. So we go over and we And every time we get that sum, which is essentially what will be on that path, every time we check if it's a target or not. Okay, so and then we call them again, call these functions for the left and for the right. They can only return 0, which is at the end. The leaf will return 0. The other values will also return 0. Yeah, so that's the list. Yeah, the path list alternative, essentially, and it's still n square, but it requires this extra memory. Okay. I would say that going through this logic a little bit faster, like a couple of minutes, could be enough overall, just to evaluate that logic. That okay, you can track the list, but because it's so easy, I mean, it's pretty straightforward. Okay, if you want to track the list, big O will be the ends, which is the worst case scenario, and so for each node you'll do that. So that's n square again. So it's kind of fast when you think about it a little bit. I mean, it could be done pretty fast, this evaluation. Yeah, you either bring that, track that list, or I don't know, there might be a little better solutions. A little better. I wonder what this one is. Yeah, I might. Yeah, I mean, let's review these solutions. That's a good exercise to read other people's code. And there's also solutions here. And oh, so there's one that's n by height. Well, it's, I don't know what they mean by height. Well, sort of by height. Oh, it's like 1,000 and, oh, they can't be. If the height is, we'll take it out as well. Let's read that one first. It's in the accepted. It's from the accepted list. So that second one, yeah. So what we have a DFS function. We have a map of integers. Count. DFS takes a root and this s integer. Answer is 0. S probably sum plus the root value, delta between this target sum, answer plus count for delta. Wow. Okay, this solution uses one DFS. So that difference, well, if there is no solution, well, there's when the difference is 0, that's when there is a solution. So wait a second. Then it goes like so. We count this this count with this for this delta. Then we say, okay, count for this specific sum plus plus. So initially the sum was 10. Okay, so we add the 10 to the map. So we run, we call left and we call right. So essentially, and it will delete this 10 out of the map, but the map will have, so all the 10s along the way, all the sum is this S is the sum of all the previous values plus the all the current value. Now the 10 plus 15. I'm trying to understand. So 10 plus 15. So yeah, at 10 we'll have the 10 in this. Then we'll put, but we'll check. We'll put, yes, S is now 15. Delta is 15 minus target sum is still 8. So delta was 2 previously, and now it's 7. And there is no 7 here, but now there is 15. So, I mean, at 10 we'll never find it, but okay, but wait a second. When at 5 we have 15. Okay, then at 5, so here sum will be 18. And then target sum is 8. So we had 10 in our count map, CNT map. There was 8, so that will count. So having 18 is the current sum. And we had 10 at some point. So in this path we had 10. So the sum minus 8. So that means that this path, the sum of this path consists of 2 parts. It consists of the target and the delta. So if we remove the delta and we do get a target, Yeah, so it checks like, okay, we have current sum, but if we remove 10, we get our, but it checks like all the possible values from the nodes. Yeah, these sums minus the target. So this in the count. Wow. So this looks like some interesting solution that uses hash map. And so this the linear time complexity solution, essentially, with some memory, but this allows to do it if it works. And well, yeah, it works because it's been submitted with a hash map. Now, if we go from 5, yeah, we check the left at 18, then that path, then we remove 3, and then we're back at 10 and 5 are on the count list, and we go to 2. So now we have 17. Now with 3, we have 18 with current sum is 18, and we do have, the delta with the target is 10, and we do have 10 in our count. So it basically, what it does, this map allows us to say if we remove the delta is the current sum minus the target minus, we have the delta plus the target, and the delta essentially is some number in the path, any number in the path. If we remove current sum, if we remove the target, or essentially, if we remove that number from the sum and we get a target, so this at 1, if we removed, let's say some number, that's where it will trigger. If I understand it correctly. We are approaching the hour, this hour. So there is it looks like there is a big O(n) linear time solution. And I might wanna, with some memory though, but it's the better on time. Well, significantly better on time. In this case, given the constraints, we were fine doing both and n square. But I think I'll review this one a little bit more to kind of get a better grasp of how they utilize this hash map to avoid, the set. They essentially, we're looking. Well, actually, we're counting those 10s as many as they are. So it's like 5 10s. We'll count them. And by the way, the answer adds all of them. So if there was 10 deltas, the answer will get 10 deltas. So if there was interesting. Well, I should review it. But that's good practice. Thank you for watching. If you like it, like and subscribe, and we'll see you in the next video.